Hello and welcome to my second video. This video is for Advanced Geometry, Chapter 2, Section 2, which is on biconditionals and definitions. So the first thing we start out with is a definition. A biconditional statement is a statement that combines a true conditional and converse. Most often we use the words if and only if to join the two statements. So the first thing we have is an example. Consider this true conditional statement. Write its converse. If the converse is also true, combine the statements as a biconditional. It doesn't make any sense to write a biconditional statement if the statement's not true and the converse isn't true. Okay, so our example, if two angles have the same measure, then the angles are congruent. And this is a true conditional statement. Okay, now from yesterday, we can do the converse if we switch the hypothesis and the conclusion. So if two angles are congruent, then they have the same measure. So if we think about that one, if two angles are congruent, they have the same measure, that's also true. And one of the things you might realize is that's one of our definitions. And this is going to really tie into our idea of what a good definition is. Okay, so both the conditional is true and the converse is true, so now we can write it as a biconditional statement. So the biconditional statement is, now at this point you can switch the hypothesis and conclusion. It doesn't matter if you start with the hypothesis or you start with the conclusion. And all you do is you put if and only if between them. So I'm going to start out with two angles have the same measure if and only if the angles are congruent. Okay, and this is my biconditional statement. I could have also said two angles are congruent if and only if they have the same measure. So now they're going to give us a biconditional and they want us to separate into the hypothesis and the conclusion. So write two statements that form this biconditional statement about whole numbers. Okay, so actually we're not separating the hypothesis and conclusion, we're separating it into basically the conditional statement and the converse. A number is divisible by 3 if and only if the sum of its digits is divisible by 3. So the easiest thing to do is write it exactly the way it appears, put the if back in the beginning, put the then between them. So if a number is divisible by 3, then the sum of its digits is divisible by 3. And then for the converse, all we have to do is switch the hypothesis and conclusion. If the sum of its digits is divisible by 3, then the number is divisible by 3. Okay. So this is that summary that we saw yesterday, kind of combines everything. Notice with the symbolic form though, what they did is now the arrow doesn't go one way, the arrow goes both ways. P is the hypothesis, Q is the conclusion, and not only does P imply Q, but Q also implies P. Okay, so this is a biconditional statement, and the example they have is an angle is a straight angle if and only if its measure is 180 degrees. Okay. The next problem we're actually going to go over in class, but I want you to take a look at it. What they do is it's a cute little activity. They show you what a polyglob is. Polyglobs are not actually anything. but they want you to take a look at the pictures they have of polyglobs and the pictures they have of things that are not polyglobs. And they want you to first identify all of the polyglobs that are in the picture. And then they want you to come up with a good definition of what a polyglob is. Okay, and we'll try this one and we'll go over it when we get to class. And all of what we've done is to get you ready for the idea of what a good definition is. Our book has good definitions, and it's going to be very important that we know something about definitions. And I'll talk about that when we get there. Okay, so 3 things that a good definition has to have. It has to use clearly understood terms. The terms should be commonly understood or already defined. A good definition is precise. Good definition avoids words such as large, sort of, almost. So this idea that, in terms of, my immediate area, my room might be large, but in terms of, the universe or, something bigger, it's rather small. So using the word large really depends on your context. So we try to avoid words like large, sort of, almost, things like that. And this is the important thing for all the definitions in our book. A good definition is reversible. That means you can write a good definition as a true biconditional statement. And what that's going to mean for us is that when we get a definition, we automatically know it's reversible, which means that when we're writing a proof, we can use a definition in our proof, even if what we're really saying is the reverse or the converse of what we're trying to say. Okay, so an example. Show this definition of perpendicular lines is reversible, then write it as a true biconditional statement. Okay, perpendicular lines are 2 lines that intersect to form right angles. Okay, so the first thing we want to show is that this is reversible. In other words, we can write the converse. So perpendicular lines are 2 lines that form right angles. So if we want to reverse this, 2 lines that intersect to form right angles are perpendicular. And that's also true, so this is reversible. So in order to make this a biconditional statement, we can say 2 lines are perpendicular if and only if they intersect to form right angles. So one of the things we want to recognize is a statement a good definition? We have to think about those clearly understood terms and things like, is it reversible? And if it says explain, what I'm really looking for is if it's a good definition, that's great. It has to have those 3 things that make it a good definition. If it's not, tell me which one of those 3 definition things it violates. Okay, so I should see something like it doesn't use clearly understood terms. It's not reversible or something like that. So an airplane is a vehicle that flies. Okay. Now, a lot of times we want to explain why it's not a good definition and say, well, there's something else that's a vehicle or that doesn't fly or something like that. But one of the first things I want you to try to do is figure out what the converse is. Because a lot of times when you think about things like, oh, there's another vehicle that flies and it's not an airplane, what you're really recognizing in your mind is it's not reversible. There's no converse. So an airplane is a vehicle that flies. Well, the first thing I'm going to do is figure out what the converse is. So if an airplane is, if something is an airplane, then it flies. The converse would be if a vehicle flies, then it is an airplane. And once I say that, hopefully you recognize that, no, wait. This is a false converse, which means this isn't reversible. As long as I can pick one vehicle that flies is not an airplane, so a helicopter or something like that, then this is not a true statement. And so what I can say is this is not reversible. So a helicopter flies, not an airplane. So this is not a good definition. Okay, and we will practice some of these in class. So this ends my, my video for today. Thank you for watching. Tomorrow we'll do that polyglobs part of it, and make sure you are okay with the notes, and then we'll work on some practice problems. Take care.